This lesson will focus on drawing covalent Lewis structures. Drawing covalent structures is different than drawing ionic structures. In the previous lesson with ionic structures, we always had the same format of 0 dots on the metal and 8 dots on the nonmetal. Covalent doesn't work that way because in covalent bonding, there is a sharing of electrons. No ions are formed. These are some general rules to go through when trying to draw covalent structures, and the more you practice them, the better you'll become at drawing them. However, it's important to notice that they will all kind of look different. They're not going to follow the same patterns like ionic structures did. While most elements will work to achieve an octet, which is 8 electrons, you must know that these 4 elements must have exactly 8. Anything past these 4 can have more than 8, and anything less than these 4 can actually have less than 8. Beryllium can have only 4 electrons or 2 pairs. Boron can have only 6 or 3 pairs. And then any element in period 3 or lower, such as sulfur or phosphorus, can actually break the octet and achieve more than 8 valence. A simple example to start with is CH4. Following the rules, we put carbon in the center because carbon is the most electronegative in this group, but also carbon always goes into the center. We put carbon with its 4 dots around it, 4 valence dots, and then we draw 4 hydrogens around the carbon in such a way that they will connect to it. Remember, nothing is forming an ion here, so don't put any pluses or minuses. The hydrogens each have 1 dot. Now I'm drawing the dots in relation to the carbon. Maybe you drew them in other positions and that's fine. I'm just drawing them to show them oriented towards the carbon. And you have to start looking at it as who is going to share however many. Carbon has 4 valence dots and it wants to get to 8, so it needs 4 more. That's why it will pair up with 4 other hydrogens. Hydrogen only wants to get 2 dots, so it already has 1. It's going to share that 1 with carbon and share another one of carbons to achieve its 2. So when 2 dots face each other that way, we get a chemical bond. And we can show that by highlighting it or circling it, or even just by drawing it as a straight line. So if I were going to redraw this structure, I could draw it like this. Each line here represents a pair of electrons, as you could see in the previous structure. I could leave it like this. This is totally acceptable as well, but more commonly, you'll see it with lines drawn. Remember that each line is 2 electrons. So if you look at only carbon, you'll notice there's 4 lines coming out of the carbons, which equates to 8 electrons, which is what it wants. And if you look at any hydrogen, there's only 1 line coming out of each one, which equates to 2 electrons, which is the number that hydrogen wants to gain. So this is an acceptable structure. This is our final answer. Another similar structure is going to be CBr4. Again, we'll start with carbon going in the center. Although bromine is more electronegative, carbon always goes in the center, as we said. We put the 4 dots on the carbon. And now we're going to draw 4 bromines around in the same pattern that we did last example. The difference is that bromines each have 7 dots on it. So I'm going to put 7 dots on each bromine. Notice the way I'm drawing it so that the single dot on bromine is facing the carbon. That's the one that wants to pair up. The pairs on bromine are already stable. They're paired up with each other. The single ones want to face out and try to bond with somebody else. Similar to before, these will now form bonds. And we have a structure that looks like that. Or if we were to redraw it again cleanly, we could draw just lines. But this time, you have to keep those 6 other dots on bromine. Those are called lone pairs. And remember that bromine had 7. Here's 2, 4, 6, and the one that it's sharing there is 7. Now it shared another one with carbon, so that's 8 total. So bromine has 2, 4, 6, and 8 on each one. and then the carbon again also has 4 lines, which is 8 dots. But every bromine also has 8 dots. Since this is called a Lewis dot diagram, remember, you still have to put these dots on it. The previous example didn't have this because hydrogen had no leftover dots, only the ones that were taken up by the bond. These lone pairs are non-bonding. They belong only to bromine. Carbon is not sharing them. Our next example is NH3. Start again by putting the first element in the center, the nitrogen, with its 5 dots. I chose to put the pair on top, but you can change that around. And then draw 3 hydrogens in position to bond with the single dots that you drew. So I'm going to put my 3 hydrogens over here because that's where my 3 dots are. If you drew it a different way, you would put them in other places. Remember, the single dots are where bonds are going to occur, not where the pairs are. Now we connect our pairs together, our new pairs, and those are now our bonds. And if we were to redraw this, it would look like this. The hydrogens each have 2, and then don't forget that the nitrogen still has its own pair on it that was not used. That lone pair on the nitrogen was not used in bonding, but it's still there, so we have to count it. And if we count total, there are 2, 4, 6, 8 on nitrogen, and every hydrogen again has 2, which is what it wants. Next, we have one of the most common examples, which is water, H2O. You never start with hydrogen in the center because hydrogen can only make one bond. So in this case, the oxygen is going to go in the center. Oxygen has 6 dots on it, 2 of which are single and 4 which are paired up. So I'm going to have 2 single spots here to form bonds, and that's where I want to put my hydrogens. Now I can pair up with the hydrogen and the oxygen to form a bond, and I get that structure. And when I redraw it, I'm just going to change the shape a little bit, and I'm going to kind of put my dots crooked like that because I'm going to draw water on an angle here. You don't have to draw it this way in terms of the shape. That is the actual way it looks, so you'll see me draw that very commonly. If you draw it as a straight line, you are okay, you can do that if you wanted to draw it like this, but you have to remember to include those 2 lone pairs on the oxygen. That is very, very important for water. It gives water its unique properties. Don't forget to put those lone pairs on the oxygen, whichever way you choose to draw this. Next up, we'll try some diatomics like O2. Here there is no center, it's just 2 atoms facing each other. But remember that they each have 6 dots on them. And since they each have 6, they want to gain 2 more or share 2 more. So we're going to form a bond in the middle there, but we're also going to form a bond there. And what that looks like is what we call a double bond. The oxygens are going to share 2 pairs of electrons between them, but they're also containing 2 lone pairs on each. So whichever oxygen you were to look at, on the left side here we have 2, 4, 6, and 8, and on the right side we have 2, 4, 6, and 8, and we now have a double bond happening between them. Following that pattern, we're now going to do N2, or dinitrogen, and nitrogen has 5 dots. I'm going to draw my dots a little differently here. I'm going to face the single ones towards each nitrogen. And remember to do your math. If nitrogen has 5 dots on it, it wants to gain 3 more. That means it's going to share 3 of its dots. And what we're going to end up getting are 3 bonds. This will be called a triple bond. So there will be 3 pairs shared between the 2 nitrogens, and then the 1 lone pair it still has on itself. So on the left we have 2, 4, 6, 8, and on the right we have 2, 4, 6, and 8. Our last example for this lesson is going to be CO2. Start by placing carbon in the middle with its 4 dots. and then drawing oxygen on either side with its 6 dots. Remember to orient the single ones towards the bond. That will help you to connect things. And this should work out very nicely. Oxygen has 6 and wants to gain 2 more, and carbon has 4 and wants to gain 4 more. Carbon has an advantage, though, that there are 2 atoms here to bond with. So carbon's going to share 2 with that oxygen, and then 2 with that oxygen. And that will end up getting 8 altogether for carbon and 8 altogether for oxygen. And when we redraw, we will get a compound that looks like this with 2 double bonds on it. And then don't forget the 4 lone pairs, or the 2 pairs, the 4 extra dots on each oxygen.